This is lecture 4B, and we're going to talk today about oxidation numbers. Now, when atoms are covalently bonded, they're not charged, they're sharing electrons. But what we can do is we can give charges to those atoms based upon where the bonding electrons are assigned. And we do this in order to help us predict products of oxidation reduction reactions. So this is going to be a tool we're going to be using in this particular unit. The type of assigned charges we're going to give to atoms in covalently bonded molecules are called oxidation numbers. This is the charge given to an atom, assuming both electrons in each bond are assigned to the atom with the greatest electronegativity. Here's how this works. If we take a compound like sulfur difluoride that has the Lewis structure that looks like this, you notice there's two bonds in the molecule. If we take the two electrons in this bond and assign it to the atom that has the higher electronegativity, which is the fluorine, and we do that for the other bond as well, then the electrons would actually be distributed like this. The pair of electrons from that first bond would go to the fluorine, and the pair of electrons here would go to this fluorine. So what would be the charges of each of these species? The sulfur, which naturally has 6 valence electrons, now only has 4. Therefore, it has a charge of +2. Because this is an assigned charge, it's not the actual charge of the sulfur, I'm not writing it 2 positive. I'm writing it +2. That's how we differentiate between charges that are assigned or pretend and charges that are actual. The actual charge, we would write 2, then the plus sign second. This is an oxidation number. It's not a real charge necessarily. It's an assigned charge based upon a little definition, and so we put the algebraic sign first. If we look at the fluorines naturally have 7 valence electrons, but they've now gained 1 additional electron to have 8. And so therefore they have an additional electron, therefore their oxidation numbers are -1. If this sounds vaguely familiar, we did something very similar back in the unit when we were learning about chemical bonding. And we were trying to come up with a technique to help us predict the best Lewis representation for a molecule. And we came up with another way to assign bonding electrons. It was called formal charge. Formal charge takes the 2 electrons in this bond and assigns 1 electron to the left atom and 1 electron to the right atom. If you assign electrons that way, you're calculating charges that are called formal charges. That's very helpful in trying to predict the best Lewis representation for the bonding in a molecule. But now when we're dealing with oxidation reduction reactions, if we're trying to predict how many electrons an element is gaining or losing in an oxidation reduction reaction, there's another way to assign the shared electrons that actually helps us in that process, and that is by assigning both the electrons that are being shared to the more electronegative atom. And when you calculate those numerical values, those are called oxidation numbers. So oxidation numbers are used to determine the number of electrons lost or gained by atoms in redox reactions. Now, you won't have to draw the Lewis structures for compounds to predict oxidation numbers. We're going to give you a little simple way to assign oxidation numbers as a series of 5 different rules, and here they are. If you ever have an elemental substance, well, elemental substances are composed of neutral atoms, so they're uncharged species. So the oxidation numbers of elemental substances, which are made of neutral atoms, always 0. If you have a monatomic ion, well, ions are charged particles, so whatever the charge of that monatomic ion is, that would be its oxidation number. So these are a little bit more obvious, okay? Here's where oxidation numbers become significant because this is where species or atoms really don't have charges. If you have a covalently bonded molecule, you have to assign oxidation numbers to each atom that are bonded. So here's how we do it. The atom with the higher electronegativity will always get a negative oxidation number because it's pulling the electrons towards it, and the atom with the lower electronegativity will get a positive oxidation number. We'll see examples of this in a minute. Fourth rule, if you have a neutral compound, the oxidation numbers will have to add up to 0, so algebraically that'll help us in assigning oxidation numbers. And similarly, if you have a polyatomic ion, the oxidation numbers will add up to whatever the polyatomic ion's charge is. Let's look at some examples. The symbol Na represents elemental sodium, which is made of millions and millions of sodium atoms. Atoms don't have any charge, so the oxidation number of elemental sodium would be 0. O-2 means an oxide ion. This ion has a charge of -2, so any monatomic ion, its oxidation number will always equal its charge. Although as an ion charge, we write it as 2-, as an oxidation number, we write it as -2. This is how elemental hydrogen exists, diatomic form. But elemental hydrogen is just hydrogen atoms. They just happen to pair up. If it's made up of elemental hydrogen atoms, oxidation number is 0. Now let's look at some compounds. Ionic compounds are pretty easy. Ionic compounds are made of ions. If you can just determine the ion charges on the periodic table, that's going to be the oxidation numbers of each of the ions in the compound. Magnesium ions are in the second magnesium's in the second column on the periodic table. Its ions are +2, and sulfur's in the 6th tall column on the periodic table. It forms ions that are -2. So the two ions in this ionic compound must have oxidation numbers of +2 and -2. For FeCl3, iron's a transition metal and chlorine is a nonmetal. This is an ionic compound. Transition metals, however, form a variety of ionic charges, so that's not intuitively obvious. We'll have to go to the nonmetal first, and based upon its position on the periodic table, chlorine always forms ions that are -1. So this compound would have 3 -1 chloride ions. If there's 3 -1 chloride ions and the charges or oxidation numbers in the compound have to add up to 0, that means the iron has to be +3. If you were going to name this compound, you would name it iron 3 chloride. So that tells you what the charge is as well as the oxidation number. So the way we write this, please notice, is that even though there's 3 chlorides in the formula, I write down the oxidation number of each ion of chloride as -1. I wouldn't write a -3 there. When people look at this, they understand this to be the oxidation number of each chloride ion, not the sum of them. For this ionic compound, metal and a nonmetal, once again, we have a transition metal, so I don't know what its charged ion is from its position on the periodic table because it can form more than one. So I'm going to go to the nonmetal first, and the periodic table predicts oxide ions would be -2. Therefore, in this compound, the copper ion would have to be +2 because the oxidation numbers, just like the charges, have to add up to 0. So these would be the oxidation numbers of the two elements in this ionic compound. Now, when we go to covalent compounds, this is just where it gets a little bit more dicey. There are no ions in a covalently bonded molecule. This is a group of nonmetals. They share electrons. So what we do to assign pretend charges, oxidation numbers, is we use electronegativities. And chlorine, being closer to the upper right-hand corner of the periodic table, is an element with a higher electronegativity than sulfur. That means it's going to get to have a negative oxidation number, and then sulfur will have to suck it up and be positive. So for the -1, you go to its column on the periodic table and go, what charge would it need to make to form an octet, a stable noble gas configuration? And for chlorine, it would be -1. So we would therefore assign each chloride ion or each chlorine atom in this particular molecule an oxidation number of -1. And because there's 2 of them, the sulfur would have to be +2. Another covalently bonded molecule, P2O5, we're going to assign the negative oxidation number to the more electronegative atom. And oxygen has a higher electronegativity than phosphorus, so we're going to assign each of the oxygens an oxidation number of -2. Okay, now you have to do a little work here. So if the oxygens are -2 each, and there are 5 of them, they add up to -10. If the oxygens add up to -10, the phosphorus have to add up to +10. So what does each phosphorus have to be? If there's 2 of them, they each have to be +5. So 2 +5s add up to 10, and 5 -2s add up to -10. Therefore, the oxidation numbers of this compound add up to 0. Here's a covalently bonded compound with 3 elements. When this happens, it's really best to recognize what element might have the highest electronegativity. It's going to be negative for sure. And which element will have the lowest electronegativity? It's going to be positive for sure. Oxygen has the highest electronegativity of any element except for fluorine. And you're not going to see a lot of compounds with fluorine in them. So almost every single time you see an oxygen in a compound, the oxygen is going to be the more electronegative element. It's going to be assigned its oxidation state that would allow the oxygen to make an octet, which would be -2. So we'll assume the oxygens in H2CO3 are each -2. Hydrogen is the nonmetal furthest to the left on the periodic table. It has the lowest electronegativity of any nonmetal, so that means it's always going to be positive when it's in a covalently bonded molecule. So hydrogen, if it's going to form a positive oxidation state, would lose its 1 electron theoretically and be +1. So in this compound of 3 nonmetals, we know the O's are going to be -2, the H's are going to be +1. And now we use the technique that the entire compound must add up to 0 for its oxidation number. So here we go. The hydrogens are +1 each, so +1 and +1 is +2. The oxygens are -2 each. -2 and -2 and -2 is -6. So if the hydrogens are +2 and the oxygens are -6, you can figure out what the carbon has to be. It has to make up the remainder of the positive charge. It has to be +4. Make sure you see how this works. The 2 hydrogens are +1 and +1. They add up to 2. The carbon adds up to 4. That adds up to 6. And then 3 -2's make -6. This makes the entire compound 0. Here's a polyatomic ion. The oxidation numbers in a polyatomic ion don't add up to 0. They add up to the polyatomic ion's charge. So the oxidation numbers of these 2 elements had better add up to -1. Oxygen is more electronegative. We would assign it an oxidation number of -2 to make it an octet. Hydrogen, if it's going to be positive, would lose its 1 electron and be +1. And a -2 and a +1 do add up to -1, so that works out perfectly. Here's another polyatomic ion. There's 2 elements. The one with the higher electronegativity is the oxygen, so it's going to be assigned an oxidation state of -2. So if the oxygens are -2 each, -2 and -2 and -2 add up to -6. So if these add up to -6, you have to think about what does the nitrogen have to be, so when you add it to -6, it equals the overall charge of -1. That's the algebra you have to do in your head. That would be +5, because a +5 plus a -2 and a -2 and a -2 adds up to -1. That's how you do oxidation numbers for polyatomic ions or groups of covalently bonded nonmetals. If we try one more like this, polyatomic ion, the oxygen has the higher electronegativity, so it's going to be -2. So each of the oxygens are -2. There's 4 of them. They add up to -8. So what does the chromium's charge have to be? Because the chromium's oxidation number has to add up to the -8 from the oxygens to equal the overall charge of -2. That would have to be +6. So now with our review of oxidation numbers, we're going to continue on with types of chemical reactions. We've learned 3 types of oxidation reduction reactions: composition, replacement, and then combustion reactions. The 4th type we're going to learn are decomposition reactions. A decomposition reaction is essentially the opposite of a composition reaction. It's one big compound breaking down into smaller ones. And there's a couple types of decomposition reactions we're going to learn. The most elementary one is just a binary compound, which means a compound made of 2 elements, decomposing into its individual elements by either heat or electricity. An example of this would be if you take the salt potassium fluoride and you melt it, we would then call that molten potassium fluoride because you'd have to heat it to like 800 degrees to melt it. So if you take molten potassium fluoride and pass electricity through it, it will decompose. Let's try to write the balanced equation for that. Potassium fluoride is Kf. If you pass electricity through molten potassium fluoride, the decomposition reaction means you're going to form elemental potassium and elemental fluorine. Elemental potassium is individual atoms because it's a metal made up of millions and millions of metal atoms. Elemental fluorine exists in diatomic form, so it would be F2. These would be the products if you decompose potassium fluoride. It's not the same thing as potassium fluoride dissolving in water and then the potassium and fluoride ions separating from each other. That's not a chemical reaction. That's just dissolving in water. If we're doing a decomposition reaction, you have to change those species from ions into atoms. To balance this equation, we have 2 fluorines on the right. We would need a 2 in front of the Kf. And to balance the potassiums, a 2 would go in front of the K on the product side. To write the phases, we said it was molten potassium fluoride. It has to be in the liquid state for this reaction to occur. If it produces elemental potassium is a solid, and elemental fluorine is a gas. Now, let's write the oxidation numbers for each of the elements in this reaction now that we've learned how to do that. This is an ionic compound. It's made of ions, so the oxidation numbers are just going to be whatever their ion charges are, which are +1 and -1. This, on the other side of the equation, is elemental potassium. That's made of neutral atoms, so its oxidation number is going to be 0. And F2 is elemental fluorine. That's made of neutral fluorine atoms, so its oxidation number is going to be 0. So you should be able to predict the oxidation numbers of any atom on any reactant or product in a chemical equation. If I write this reaction out a little bit more explicitly to show the charges, and here you can see the potassium and the fluoride ions are +1 and -1, and the potassium and fluorine on the product side are neutral atoms. Now let's see if we can predict what's being oxidized and what's being reduced like we did in our last lecture. The oxidation is always when an element has its charge going up. So which element has its charge going up? That's going to be the fluorine. It's going from a -1 charge up to 0. So we would say the fluorine is being oxidized because its oxidation number is increasing from -1 up to 0. The reduction is going to be the element whose charge goes down. Potassium is going from +1 down to 0, or you can see the oxidation number is going from +1 down to 0. So that means the potassium ion is what's being reduced because its charge is being reduced from +1 down to 0. There's a second type of decomposition reaction I would like you to know, and it's a more complex one. It's the decomposition of a compound called a metallic chlorate. And metallic chlorates decompose when heated to form metallic chlorides and oxygen. And we'll do one example of this for you. If we take the compound lithium chlorate, and that's what a metallic chlorate would be, it's any metal ion bonded to a chlorate ion. So lithium chlorate would have this formula. Lithium ions are +1, chlorate ions are -1, so it's LiClO3. If you heat this up, what you actually do is you drive all the oxygen off. So that means if the oxygen is removed, you wind up getting a metallic chloride, just lithium bonded to chloride, then plus oxygen gas. So the products would be lithium chloride, whose formula would have to be LiCl because the ion charges are +1 and -1, and you get elemental oxygen. Isn't it tempting to go, I should maybe put O3 here because that would balance the equation, but that's not what happens. We're going to actually do this in one of our experiments. You don't get ozone produced, you get oxygen. So you can't change the facts. Unfortunately, though, this reaction doesn't look good just because it's not balanced yet, so we have to balance it. Now, because we have 3 O's on the left and 2 O's on the right, you need a common multiple of 6. So I'm going to put a 2 here to get 6 oxygens on the left, and a 3 here to get 6 oxygens on the right, and now the oxygens are balanced. To balance the lithiums and the chlorides, we need a 2 here. Now we have a balanced equation that produces a metallic chloride and oxygen gas. The lithium chlorate is a solid. It's an ionic compound. They all have high melting points, so they're going to be solids. The lithium chloride we would predict would be a solid because that's an ionic compound as well that has a high melting point, and oxygen is a gas. Let's do the oxidation numbers now here. This is an ionic compound. So lithium ion's charge can be determined from its position on the periodic table. It has to be +1. This is a polyatomic ion, so now we have to use the electronegativities to predict their oxidation numbers. Oxygen has a higher electronegativity than chlorine does, so it gets to be negative, and we're going to assign oxygen an oxidation state of -2. So now, realizing the whole thing must add up to 0, if the lithium is +1, and the O's are -2, -2, -2, which add up to -6, you have to figure out what does the chlorine have to be so they can all add up to 0, and that would wind up being +5. It has to be. In the next compound, lithium chloride, this is a simple ionic compound. The ionic charges can be predicted from their columns on the periodic table, and those will equal their oxidation numbers. So these will be +1 and -1. And then oxygen is in its elemental state. It exists as individual atoms, which just happen to bond together to make diatomic molecules, but it's still made of oxygen atoms. So the oxidation state of atoms are 0. With this, we can predict what's being oxidized and reduced. And this is why oxidation numbers are relevant. When you have covalently bonded units, it's hard to tell who's gaining and losing electrons. But with oxidation numbers, you can tell rather easily. In this case, the oxygen in the reactant has an oxidation state of -2, but on the product side, it has a state of 0. It's going up. That means the oxygen is the element being oxidized in this reaction. So the O is being oxidized because its oxidation number increases from -2 up to 0. The chlorine has an oxidation state of +5, and then on the product side, it's -1. It's going from +5 down to -1. That's being reduced. So we've identified the chlorine as the element being reduced in this reaction because its oxidation number is going down from +5 to -1. The lithium happens to not be changing its oxidation state in this reaction. So those first 4 types of chemical reactions were all oxidation reduction reactions. We're now going to talk about a couple of non-oxidation reduction reactions. These are reactions in which atoms do not gain or lose electrons. They're essentially the reactions between ionic compounds, which exist as ions, which are stable because they have octet configurations. They just rearrange who they're bonded to. And the first type of non-oxidation reduction reaction we're going to deal with are precipitation reactions. The general form is going to be 2 ionic compounds reacting with each other, AX plus BY, and you just switch their partners. And if you switch the partners and you happen to form a solid, then that would be called a precipitate, and this would be a precipitation reaction. So a precipitate is defined as a solid that's formed when 2 solutions are mixed. And when will a solid form? Well, that's if you have 2 ionic compounds dissolved in water in a solution, and if an ion from one compound and an ion from the other compound happen to have a strong attraction for each other, they may bond and they may come out of solution and settle out as a precipitate or as a solid. And this is why you will need to have handout 6 available, because handout 6 talks about how you predict whether positive and negative ions will combine together to precipitate out of a solution. And so we're going to go through the solubility rules on handout 6 now for you so that you'll be able to predict if a precipitate forms in a reaction that looks like this. So a precipitate is an insoluble compound. And quantitatively, that actually has a meaning. Insoluble ionic compounds are compounds whose solubilities are less than 0.1 grams that are dissolved in 100 grams of water. So they actually could dissolve in a microscopically small amount. But if it's so small that it's fairly negligible, we call those compounds insoluble. Something that's soluble in water is defined as anything who will dissolve more than 1 gram per 100 grams of water. Sodium chloride is like this. You can dissolve 50 grams of sodium chloride in 100 grams of water at room temperature. So these are called soluble salts. You notice there's a little gap in there. We're going to ignore the gap for this semester, but if your solubility is between 0.1 and 1, you are called partially soluble, and that's a gray region that we're not going to deal with at this time. But we'll assume that ionic compounds either fit into the soluble realm or the insoluble realm, and we want to tell you how you predict that. So there are 5 solubility rules for dissolving ions in dilute solutions. And if you're a biology major, you can just memorize these rules and you'll be fine. But if you're an engineering major, let me give you some reasons for why these rules are what they are, and maybe the common sense behind them will allow you to actually do a little bit less memorization than completely necessary. Here we go. These are rules for dissolved ions in solutions. If you put ions in solution, the question really is, will they precipitate with something else? Will they bond with some other ion and settle out as a solid? And the first rule is, if you have a group 1 ion or an ammonium ion, they will never precipitate out of solution with anions. They will never bond to an anion and precipitate out, as long as the solutions are considered to be fairly dilute, and we'll assume all dilute solutions throughout this unit. So this means sodium ions, lithium ions, potassium ions, ammonium ions, they never will precipitate out. What's similar about all of them? They have a charge of +1. So how strongly can a +1 charge attract to an anion? Not very strongly, because that's the lowest possible charge there is. So when you have really low charged positive ions, they do not attract to negative ions strongly at all. So therefore they don't stick to them, and they don't bond together to make solids, and they don't settle out of solution. With that in mind, look at this rule. Nitrate ions and acetate ions that are in solution never precipitate out with cations. How come these would never form a precipitate? Well, it's their charge. Their charges are only -1. They're the lowest possible charges possible. So they don't attract strongly to positive ions, so they won't stick to them, so they won't form solids, so they won't make precipitates. Third rule, same concept. Chloride, bromide, and iodide ions will never precipitate out of solution with cations, and the reason that you learn this rule is conceptually because their charges are only -1. They don't stick very strongly to positive ions, so they won't make solids, they won't precipitate. Now, if you notice, what's missing from this rule is fluoride. Fluoride's not in this rule because even though it has a -1 charge, the ion size is really, really small. So this is one thing that happens when you have low charged ions. If they happen to be really small, that concentrates their charge, and it means they can actually get closer to the oppositely charged ions in the solution, and the closer you get, the stronger the ionic bond. So small ions with charges of either -1 or +1 could actually precipitate. And so because fluoride ions do precipitate with a variety of different cations, it's not included in this rule. The ion is so small, that's why it's not included. There is an exception to this rule that you will need to know, because chloride, bromide, and iodide will make precipitates, but they'll only precipitate with silver ions, mercury 1 ions, or lead 2 ions. So you're just going to have to memorize silver, mercury, lead will precipitate with chloride, bromide, and iodide. The reason this happens is that silver, mercury, and lead have fairly high electronegativities for metals. And because their electronegativities are fairly high, when they actually bond with chloride, bromide, or iodide, the bond is not completely ionic. It's slightly covalent, and that causes a greater tendency for them to stick together. And so you wind up getting silver with chloride, or mercury 1 with chloride, or lead 2 with chloride, forming slightly covalent compounds, so they stick together, and therefore they precipitate out of solutions. So you will see precipitates with chloride, bromide, or iodide ions, but only with silver, mercury 1, or lead 2. Next rule, sulfate ions never precipitate out of solution with cations. Why would this be? It has a -2 charge. That's a high charge. That should stick strongly to positive ions. Well, it's because an SO4 ion is so big. So even though it has a higher charge, its big size does not allow it to get close to positive ions, so it doesn't precipitate out. There is an exception to this rule you need to know. And that exception is sulfates will precipitate with the mercury 1 ions, with lead 2 ions, and then from the second column on the periodic table, these go right in a row: calcium, strontium, barium. So these two exceptions, whether you're a biology or an engineering major, you're just going to have to memorize. The last rule has to do with the ions that tend to make lots and lots of precipitates. Carbonate ions that have a high negative charge. Hydroxide ions, which are really, really small. Oxalate ions, which have a high charge. Phosphate ions, which have a high charge. Sulfide ions have a high charge. They do precipitate out of solutions with cations. They make lots of precipitates. If they're in a solution and they bump into a positive ion, they're going to stick because they make a strong ionic bond, and they'll precipitate. There's an exception to this. The exception is rule 1. They do not precipitate with group 1 or ammonium. Those are the only ones they don't. So this last one's maybe the most complex one for you to have to memorize. So I don't know what you're going to do. Maybe come up with some mnemonic. I don't know how you're going to remember carbonates and hydroxides and oxalates and phosphates and sulfides always precipitate. I'll leave that up to you to figure out a way to remember that rule. Let's try some examples then. Let's say we're mixing together solutions of potassium sulfate and barium chloride. Will a reaction occur? And if it does, let's write the equation for that. So potassium sulfate would be K2SO4 and barium chloride BaCl2. These would be your reactants. This is the characteristic look of the reactants for non-oxidation reduction reactions. It's two compounds reacting with each other. think back to all the other types of reactions we've learned. The composition reactions were an element plus an element. Replacement reactions were an element plus a compound. Combustion reactions, a compound plus oxygen. A decomposition reaction was only one reactant. It was a compound that decomposes. Now, if you have two ionic compounds reacting with each other, this is not going to be an oxidation reduction reaction. This is going to be a non-oxidation reduction reaction. And we tend to call these exchange reactions because what you do is you just switch the partners. You exchange the ions, and then you have to analyze the products with the solubility rules to see if one of them makes a precipitate. So each ionic compound is made of a positive ion and a negative ion, a positive ion and a negative ion. When you switch the partners, you make the positive ion in the first, go with the negative ion in the second, and the positive ion in the second go with the negative ion in the first, just like foiling in algebra. So that means the two predicted products would be potassium with chloride. And notice I didn't write K2Cl2. That's not the formula of potassium chloride. Potassium ions are +1 and chloride ions are -1, so it's KCl. Barium then goes with sulfate, and barium's +2, sulfate's -2, so the formula is BaSO4. You don't write it SO4Ba, you always write the positive ion first, the negative ion second. So these are our predicted products. We can balance the equation by having a 2 in front of the KCl to balance the two potassiums, and then a 2 in front of the barium sulfate. Oh no, that's it. That actually balances there. Sorry. The 2 there balances the two potassiums and the two chlorides. We now have a balanced equation written. Just because we've written on a piece of paper doesn't mean the reaction actually occurs, though. An exchange reaction like this, where ionic compounds switch partners in solution, will only happen if one of the two products is a precipitate or is insoluble with water. So we're going to have to use the solubility rules to predict this. This is an ionic compound that contains potassium. And the first rule says potassium ions never precipitate with anions. So that means this first compound will be aqueous. It will not bond together. The ions will stay separated. And when they're separated from each other, the phase is aqueous. The second compound has sulfate in it. And the rule for sulfates were sulfate ions never precipitate with cations except mercury, lead, calcium, strontium, and barium. So therefore, BaSO4 will actually bond together to make a solid precipitate. Therefore, a reaction occurs between these two reactants. If we write the phases, they told us we were mixing solutions of potassium sulfate and barium chloride, so they'll tell you the phases of the reactants. You have to predict the phases of the products. Potassium ions never precipitate with anything, so KCl would be a soluble compound. Sulfates precipitate with barium, so barium sulfate would be an insoluble compound. This is your balanced molecular equation. And because this equation involves soluble ionic compounds, which are strong electrolytes, we'll have to write this in ionic form and then net ionic form. The potassium sulfate, when it dissolves in water, would dissociate into 2 potassium ions and 1 sulfate ion. The barium chloride, when it dissolves in water, would dissociate into 1 barium ion and 2 chloride ions. Over to the product side. Potassium chloride would dissociate into 1 potassium ion and 1 chloride ion, but because there's a 2 in the balanced equation, you distribute the 2 to both of those, and this balanced equation will show 2 potassium ions and 2 chloride ions. And then here's the significant difference. If you have something that is insoluble in water, it's a solid. That means the ions don't dissociate, they stay bonded together. So we leave the BaSO4 bonded together and write it as a solid. This is your ionic equation. In this ionic equation, there are 2 sets of spectator ions. The potassium ions are the same on both the left and the right side, and the chloride ions are the same on both the left and the right side, and there's the same number of them, so they have to be that way. So what's left over is going to be your net ionic equation. It's the sulfate ion from the first solution mixing with the barium ions from the second solution, and when they bump into each other, they precipitate out as BaSO4. Now, let's check the oxidation numbers of all the elements in this equation. First, we have a covalently bonded polyatomic ion. So if we're doing oxidation numbers, you have to use electronegativities. Who has the higher electronegativity? Oxygen. So oxygen gets an oxidation number assigned to it of -2 because it's more electronegative. So if oxygen's -2 and there's 4 of them, 4 negative 2s would add up to -8. So what does the sulfur have to be? So when you add it to -8, it adds up to the overall charge of -2. That would have to be 6. So the oxidation number of sulfur is 6 in the sulfate ion. The O's are -2 each. The barium ion is just its charge, +2. And then in barium sulfate, this is an ionic compound. Barium's charge comes from its column on the periodic table. It's +2. This is the covalently bonded polyatomic ion, so we use electronegativities. Oxygen has a higher electronegativity than sulfur, so it's going to be assigned an oxidation number of -2. And there are 4 of them, so the 4 oxygens add up to -8. The barium is +2, so you have to go 2 for barium, -8 for oxygen. What does the sulfur have to be? So the whole thing adds up to 0, and that has to be 6. So now if I ask you what's being oxidized and what's being reduced here, the answer is nothing. The sulfur stays +6 throughout the reaction. The oxygen stays -2. The barium stays +2. Precipitation reactions are not redox reactions. No electrons are being gained or lost. It's just ions from different compounds who have a strong affinity for each other will stick together, and they will actually form a solid when they're mixed together in a solution. Let's give you one to try to do now on your own. See if you can write the balanced molecular equation, predict what the precipitate is from the solubility rules, then write the equation in ionic form, then net ionic form. The one you're going to work on is the mixing of solutions of magnesium chloride and silver nitrate. Mixing together solutions of magnesium chloride and silver nitrate. So the correct formulas for the reactants are MgCl2 and AgNO3. Characteristically, when you have 2 compounds, you're going to assume it's going to be an exchange reaction. The compounds are going to switch partners, and we're going to look to see if one of the products, according to the solubility rules, is insoluble and will form a precipitate. When you switch the partners, magnesium will go with nitrate. Magnesium ions are +2, nitrate ions are -1. The formula is MgNO3 taken twice. Silver will go with chloride. Silver ions are +1, chloride ions are -1, so the formula is AgCl. So these would be the correct formulas of your 2 products. Now we have to balance the equation. 1 magnesium on the left, 1 magnesium on the right. 2 chlorides on the left, only 1 on the right, and so a 2 will go in front of the AgCl. To balance the nitrates, which there's 2 of them on the right, we'll put a 2 in front of the AgNO3, and that balances the nitrates, and now the silvers are balanced as well. This is our balanced equation for this reaction. Now, does a reaction actually occur? Just because you can switch partners on a piece of paper doesn't mean that these 2 solutions will actually do anything when you mix them together. So we have to use our solubility rules to predict. Now, they already told us that the 2 reactants were in solutions. Let's now apply the solubility rules to the products. The first product contains a nitrate ion. Rule number 2, nitrate ions never precipitate with cations. So that means magnesium nitrate will not be a precipitate. It has to be aqueous or soluble. The second product is silver chloride. The rule for chloride salts is that chloride ions never precipitate with anything except silver, mercury, or lead. So this is one where chloride does precipitate. That's going to be a solid. This is why a chemical reaction occurs, because when you switch these partners, one of the products is insoluble. To write this in ionic form, we would dissociate each of the soluble ionic compounds because they're strong electrolytes. Magnesium chloride should be written as a magnesium +2 ion and 2 chloride ions. Silver nitrate dissociates into a silver ion and a nitrate ion, but because there's a 2 in the balanced equation, you have to double each of those, and you're going to have 2 silver ions and 2 nitrate ions. On the product side, the magnesium nitrate will dissociate into 1 magnesium ion and 2 nitrate ions. And then the whole point of this, the precipitates are solids. They don't dissolve in water. They don't dissociate. They stay bonded together. So it'll be 2 AgCl solid. In this ionic equation, the magnesium ions cancel out and the nitrate ions cancel out. So you're left over with 2 chloride ions aqueous plus 2 silver ions aqueous yields 2 AgCl. And if you ever have a net ionic equation where all the coefficients are divisible by an integer, divide them all by that integer, in this case 2, and the final net ionic equation would be silver ion plus chloride ion yields AgCl.